Good afternoon. It's Friday, so we're doing some statistics. We've been talking about probability now for a few weeks, and I hope that you're finding it valuable. I think probability is really at the heart of the intro statistics curriculum here, and it really helps a lot to get a firm understanding of probability as you move forward into distributions and then finally into hypothesis testing. I'm sure some of your classes are nearing talking about hypothesis testing if you're not already doing it. And we will get there as well, but I do think that really understanding probability well is incredibly important to managing what hypothesis testing is all about. And so what we're going to talk about today are probability questions for the deck of cards. So your standard deck fifty 52 cards. Each has a value and a suit. So the values are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then jack, queen, king. The suits are clubs, spades, hearts, diamonds. Now, like what we've been talking about for a few weeks with the spinner, with the dice, we're in a theoretical probability space, right? For a lot of these standard setups where we're talking about, yes, the deck of cards is a physical object that we know about and maybe have done things with, but in a theoretical space, it's also helpful in order to play out some of these probability concepts. So what does this mean? Well, let's start. Let's take the experiment of drawing one card. At random. So the probability that you get, say, a club, meaning that tends to be shorthand for the probability that the suit is club. Well, it's 1/4. Each of the suits, clubs, spades, hearts, and diamonds, has each of the values, ace through king, 13 values. And no extra, so they're all equivalently likely. Okay, that's kind of a hallmark thing of the theoretical probability space for a deck of cards. There's no stacking of the deck, right? They are each of these 52 cards is as expected, and therefore there are 13 clubs, 13 spades, 13 hearts, and 13 diamonds. So the probability when you draw one at random of being any particular suit is equally likely 1/4. Kind of through a similar set of reasoning here. The probability of getting a jack, right? You've drawn a card and having it be a jack is 1 out of 13. I want to pause here for a second because what you might notice is that 1/4 and 1/13 can interact in a quite interesting way. And in the same sort of sensibility, the suit and the value can interact in an interesting way. And that way here is that they are independent. So we can talk about the probability that on your draw you get the jack of clubs. I mean, there's one way to think about this which says list out the 52 cards and look for the jack of clubs. There's only one, so it's 1 out of 52. Another way of thinking about this is that this is the probability of a jack and club. So we want to start thinking about conditions in this way at times, where this is a kind of a joint probability. We're saying that it's a jack and it's a club, the jack of clubs. So we might label something. The more specific that label is, sometimes you can break that down into its component pieces and talk about probability there. So that, because they are independent, why are they independent? What is the kind of earmark for this? Well, we need to think about conditional probability seriously to establish independence, which means essentially, like, if you have a jack, is it because of the virtue of being a jack, does it change the likelihood of the suit of the card? And by design for these kind of standard decks of cards, no, it does not, right? The likelihood of, if you have a jack, the likelihood of any suit is 1/4. Similarly, if you have any suit, the likelihood of a jack is 1/13. Therefore, the interactions here are independent and we can multiply them together. Well, that should be contrasted with this type of thing. The probability of a jack or a club, a compound probability here. We're thinking about drawing a card, say a shuffled deck of cards, so the top is random. We take that top card and we look at it and we say, okay, what is the probability that this was going to be a jack or a club? Well, this we need to remember from the additive rule, which we covered last time, right? It is not equal to 1/13, the probability of a jack, plus 1/4, the probability of a club. Why is it not equal to that? Remember from the additive property that we talked about. Well, it's because you don't want to double count. If you add them without attending to the question of whether a card could be a jack and a club at the same time, then you will be double counting. In both categories, when we're counting this 1/13 and 1/4, the jack of clubs is in both of those calculations when it comes to a success. But the jack of clubs isn't more likely just because it's a jack and a club, right? It's still equally likely 1/52 chance of getting a specific card. So we need to, now I can reset this and say this is equal, we need to subtract the joint probability. So this is equal to the probability of a jack plus the probability of a club minus the probability of a jack of clubs. Now, I want to be very careful here. In the past, I've had students get stuck on this kind of formulaic way of thinking about the additive property and saying, well, why are we taking out the jack of clubs? Isn't it a success here? It's a jack and a club. So, and the answer again is yes, definitely it is. So we're not saying that the jack of clubs doesn't count or isn't part of the successes for this event. What we're saying is that if we only look at this and this, the probability of a jack and the probability of a club, we are double counting the jack of clubs. So when we subtract this here, we are just removing the double counting, not both of them, right? Just one of the doubles. So it's a tricky thing for sure. I think it's another thing that's useful to see as a table, a cross table, where if we take a second here, let me give myself a little more space. Okay, and we cross that with clubs, spades, diamonds, and hearts. What are we talking about for successes here? Well, the jack of clubs, jack or club. So all of this and all of this. And note that the jack of clubs right here is double counted. You see the intersection. So we subtract exactly once. So we can think almost about like it's already been counted, so all we want to do is add these three as successes. Okay. This type of diagramming for yourself can be very, very useful. I think visually it's definitely helps me to understand what we're talking about when we have these cross characteristics, say, of a card. But also when we did the sum of the two six-sided dice, that's a useful one as well. Okay. Now let's see. Let me do a little erasing. Let's talk about a couple more compounded probabilities here. So probability of a jack or a queen. What we want to know about the additive property is that it is always the case. The additive property is always working. What's useful about this is that if there is no danger, if there is no double counting, so if there is nothing that is both of the characteristics or all of the characteristics that you're curious about, then you won't have to worry about it because it will be 0 in the AND statement. So for example, this by the definition or by the additive property is this. It is the probability of a jack separately plus the probability of a queen separately minus the probability of a jack and a queen. So if there's such a thing as a jack and a queen, it'll be in both of the first two categories and the second one, or the last one, the third minus statement, but that will be counteracting the double counting. So what is the probability of a jack? Well, it's 1/13. What is the probability of a queen? It's 1/13. There are 4 of each. It may be useful to see this as well like this. Frequently using unsimplified probabilities during the calculation can be illustrative because there are 4 jacks out of 52, so we remember like what we're talking about. But in essence, the ratio of jacks, right, the frequency of jacks is 1 out of 13, 1 for each of the 4 suits. So 4 out of 52, 1 out of 13. But minus 0, because a card cannot be a jack and a queen at the same time. So we get, when all is said and done, 2/13. Okay. Let's see, a couple more. Let's talk about conditional probability. I think that's where we really get into the richness here. So the probability of a club given that the card is a jack, right? Well, let's think about it. This is where the beauty of independence interacts now with conditional probability, right? The fundamental idea here about conditional probabilities is that if you have this piece of information that is known, does it affect the likelihood of another piece of information that is unknown? And the question here is sort of, it's useful to think in those terms. If you know that the card is a jack, does it change the likelihood that it's a club? The answer is no, right? It does not. So the probability of being a club given that it's a jack is exactly 1/4. Now that should be contrasted with something like, what is the probability that the card is a queen given that it's a jack? Those are not independent observations, right? If you know the value of the card is jack, you actually also then know that the value of the card is not a queen. Right? The value of the card, knowing the value of the card, affects the likelihood of other values, but it does not affect the likelihood of other suits. So the probability that a card is a queen given that you know that it's a jack is 0 because you know it's a jack, it's not a queen. And in a similar kind of set of thinking, the probability that the card is a jack given that the card is a jack, right, is exactly 1. You already know that it's a jack. This is known information. So you're then asked about the value, whether it's a jack. Well, yes, it is. I know it is. Right? These are really useful kind of theoretical questions to answer for yourself. To understand conditional probability in this way is very, very powerful, because as we move forward into hypothesis testing, we are very frequently thinking in terms of a conditional probability or an assumed conditional probability, even down to the line of saying, we're assuming this probability distribution, and therefore what changes. Conditional probability is really, really powerful. It's a tool that we should work on developing a lot in this course here. Let's see. Let's change the experiment. Well, same deck of cards, but the experiment draw one card, look, draw second card. Without replacement. Now this phrase, very, very common when it comes to card probability. Similar with the bag, the marble probability that we did early on, where there's kind of two experiments that are really useful to consider beyond the sort of baseline experiment of drawing one at random. And those experiments are generally drawing two at random. And in one case, you draw both. And in the other case, you draw one and then put it back and then draw a second time. As you can imagine, when you replace, right, the replacement situations, replace is almost a misnomer, or at least it's not as helpful as maybe the word reset, right? So if you're replacing the card into the deck, you're actually resetting the experiment to the same one that you just did, right? If you've drawn the Jack of Hearts, you put it back into the deck and reset the experiment with another shuffle, well, then the likelihood of all your cards is exactly the same as it was for the first draw. This, however, is much more powerful, right? You're not resetting. You are altering. You're altering the probabilities because you've taken an outcome out of the deck. So for example, the probability that the second card is heart given first is spade. Okay, now let's think about this. Let's think about this. What has changed? Can we voice it? Okay. We have, well, how are we starting? We have a shuffled deck randomly of 52 cards. Those cards each have a value and a suit. Any of 13 values, ace through king. Any of 4 suits, clubs, spades, hearts, diamonds. We can list them. We can list them. The sample space here. We can, for example, talk about the 6 of spades. Right? We can talk about any of the 52 cards that occur at the intersection of value and suit. What is happening here when we're talking about without replacement experiments? We'll visualize it, right? In this deck of cards face down that we don't know about, they're randomized. Any card could be in there when we draw. They're all equally likely. But if you take one out and you know which one it is, you are literally, you've taken it out of the equation for the next draw. So the probability calculation changes. So for example, what is happening here? Well, we know we want to calculate the probability that the second card is a heart given that the first is a spade. Okay. What does that mean? So really what we're thinking about is 2 aspects here, which is the number of hearts, successes, and the number of overall cards, right? So we're thinking, we want to know like what proportion of all the cards are hearts as opposed to something else, some other suit. Well, there were 52 cards. You can see them here cross-tabulated. And you can find some really great ones online where it actually lists them all out and shows them, but it's not worth necessarily recreating. This gives an idea of like we're able to cross here, so like the 9 of spades. Now what we know here about the first card that we've drawn, what information do we know? So this is the kind of thing where we really want to go into kind of the theater of the mind and say, okay, why don't we know what exactly the card is? Why do we only know that it's a spade? Well, imagine like you've shown it to somebody else and they're going to tell the truth to you and they say it's a spade, but they don't tell you which number it is, right? So it could be the 9 of spades, could be the 4 of spades, could be the ace of spades, so on. But you do know that it is a spade, and you also know that it's out of the deck. And so what has happened is that one of these 52 cards is no longer in the deck. And that card is not a heart. So there are still 13 hearts. There were 13 hearts, there are still 13 hearts. There were 52 cards, there are 51 cards. So this is a 13 out of 51, a little bit more than 1/4, which should make sense. It's a little bit over than 1/4. Why? Well, in the original setup, there are equal number of cards for each of the 4 suits, but now there aren't. Now, the 3 suits, hearts, diamonds, and clubs, all have 13, but there are only 12 spades left on the second draw. How about the probability the second card is a spade given first is the jack of spades? This is even maybe more illustrative in this visual here. Now we know precisely which card it is that came out on the first draw. It's the jack of spades. That card is no longer in there. All the other 51 cards are. There used to be 13 spades, now there are only 12. So what we're approaching here is being able to really understand, I think, or grapple with what the conditional probability looks like. It's if you know information, you may alter the likelihoods. So what we can think about is the probability that the second card is a heart, given first is spade, 13 out of 51. Probability second is diamonds, given first spade, 13. Clubs, given first spade, 13 out of 51. Probability second card is spade, given the first is spade, 12 out of 51. Add those up, probability space, 51 out of 51. There are 51 cards left in the deck. Right? You've taken one out. Let's do a couple more. The probability that the second card you draw is the ace of hearts, given that the first is the ace of diamonds. And here what I want you to really consider is the fact that we're talking about an ace in both cases, right? An ace of a different suit. So the probability that the second is the ace of hearts given the first is the ace of diamonds. And here's specificity really coming to bear again. Knowing that the first is the ace of diamonds lets us draw the X very accurately, right? We know that it's not that card is out. So it doesn't, there's no likelihood now that on the first draw we took out the ace of hearts. If there were, that would be a question we need to grapple with. We know exactly what card we took out. We know there's exactly one ace of hearts left out of the 51 cards. Now we should confront then this question, and we'll leave it here for you to think about. What if you're asked, so you've shuffled the cards, every card random, hold it out, person draws a card, they look at it, you ask them what the value is, they say, the card I have is an ace. And you then want to think about, you're about to draw one, what is the likelihood you get the ace of hearts? Well, here we're in a situation where I think hopefully it's clear that the number changes. First you drew a card, so there are fewer cards left. You also drew an ace, so there are fewer aces left. However, it's possible that you drew an ace that is not a heart. And it's possible that you drew the ace, that your partner drew the ace of hearts. If they drew the ace of hearts, then your likelihood of drawing the ace of hearts is 0. If they did not draw the ace of hearts, if they have the ace of spades or the ace of clubs or the ace of diamonds, then your likelihood of the ace of hearts is still 1 out of 51. So we have this interaction here to be considering where we don't know what their card is precisely. There's a chance that it could be our card that we want. There's a chance that it's one of 3 other cards that we don't want. The ace of clubs, the ace of spades, the ace of diamonds. And so in the calculation here, we're going to have to think through that. What does that mean? How do we compensate for the fact that there are these different possibilities when it comes to this conditional probability, where in one case it breaks the conditional probability to 0, in another 3 cases it takes the conditional probability to 1 out of 51. How do we want to